Module 5, Session 2. Session 2 will cover Learning Outcome 3.3.5, Solving Problems in 2D and 3D using the Sine and Cosine Rule, Part 1. Learning Outcome 3.3.5, Solving Problems in 2D and 3D using the Sine and Cosine Rule, Part 1. Our next section is using the sine and cosine rules to solve problems in 2 and 3 dimensions. Students were introduced to the sine, cosine, and area rules in Level 3. In Level 4, these rules will now be applied to solve more complex problems in 3 dimensions, not just 2 dimensions. The area rule is not included for Level 4. Students should remember from previous levels that when we are working with right-angled triangles, we use the theorem of Pythagoras and the trigonometric ratios to find lengths and angles. When the problems involve triangles that are not right-angled, they need to use the sine and cosine rules. Let's look at an example using a right-angled triangle. This is revision from Level 3. Calculate the unknown angles and sides of triangle ABC in the figure. We know that sine A is equal to the opposite side over the hypotenuse. This is our trig ratio. We can substitute in our values of 50 and 100 for O and H, which gives us a half. Using either our calculator or our special triangles, we find angle A equals 30 degrees. Now we have 2 angles of the triangle. We know that the angles of a triangle sum up to 180 degrees. So we can say that angle B equals 180 degrees minus 30 degrees minus 90 degrees, which gives us 60 degrees. We have the lengths of 2 sides already. AB is 100 millimeters and BC is 50 millimeters. Using the theorem of Pythagoras, we find that AC equals square root of 100 squared minus 50 squared, which gives us 86.6 millimeters. Before we revise the sine and cosine rules, please work with a partner to do this activity to find missing angles and lengths in triangles. Then take some time to discuss the challenges faced teaching the sine and cosine rule and 2D or 3D problems. Let's run through the solution to the activity. Calculate the unknown sides and angles in this diagram. Let's start with triangle ABD and try to find side BD. We know that sine theta is opposite of hypotenuse, so sine 40 degrees equals BD over AB. Rearranging, BD equals AB times sine 40 degrees. Using our calculator, we get 4 times 0.64. which gives us 2.57 meters for BD. Next, let's find the last missing side in triangle ABD, which is AD. We know that cos 40 degrees equals AD over AB, because this is adjacent over hypotenuse. Making AD the subject of the equation, AD equals AB times cos 40 degrees, which equals 4 times 0.766, so AD equals 3.06 meters. We have 2 outstanding angles in triangle ABD. We know that ADB plus BDC equals 180 degrees because they are adjacent angles on a straight line. So angle ADB is 90 degrees. Because all the angles of triangle ABD are supplementary, ABD equals 180 degrees minus 90 degrees minus 40 degrees. We can conclude that ABD is 50 degrees. Now, let's consider triangle BCD. We have 2 outstanding angles. The big angle ABC is given as 90 degrees. So, DBC equals ABC minus 50 degrees, which gives us DBC at 40 degrees. Now, DCB equals 180 degrees minus 90 degrees minus 40 degrees, because the angles of a triangle sum up to 180 degrees. Therefore, DCB is 50 degrees. Now we turn to triangle BCD to find the two remaining sides. Let's find BC first. Sine 50 degrees equals BD over BC, opposite over hypotenuse. Making BC the subject, BC equals 2,57 over sine 50 degrees, which equals 3,35 meters. Lastly, we need to find CD. Cos 50 degrees equals CD over BC. So CD equals BC cos 50 degrees. We substitute and get a final value of 2,15 meters for CD. Now, if our triangle is not right-angled, we cannot use Pythagoras or the trig ratios. We can, however, use the sine rule, also called the law of sines, which students should remember from level 3. The sine rule holds for all triangles, acute, obtuse, and even right-angled triangles. It is a good idea to get students used to labeling a triangle in the way shown, with the side labeled with a small a opposite angle A and the small b opposite the angle B. This helps them to look for the correct information in a given problem. Let's take a look at the rule. To calculate a side, we use a over sine angle A equals b over sine angle B equals c over sine angle C. To calculate an angle, we use the reciprocals. Sine angle A over A equals sine angle B over B equals sine angle C over C. We can see why lecturers often call the sine rule the rule of opposites. The sine rule formula is on the exam formula sheet. Only one version of the sine rule is given. Students should realize that they can invert the fractions. We need at least 3 pieces of information on a triangle to start finding missing angles and sides. When students are deciding whether to use the sine rule or the cosine rule, they need to establish what information they have. The sine rule is used when we have 2 angles and a side, angle side, or angle side angle, or when we have 2 sides and a non-included angle, side angle. Looking at this more closely, given 2 angles and 1 side, we can find the unknown side C with the sine rule, solving for C. Or, given 2 sides and a non-included angle, we can find the unknown angle B with the sine rule, solving for angle B. If you highlight the information given, you'll see it forms a cross shape on the triangles. The sine rule is often called the rule of opposites, as we mentioned earlier. If we have 2 sides and an included angle, the sine rule is not going to work. In this equation, the given information is shown in blue. As you can see, we can't set up a proportion as we don't have enough information. Let's work through an example. Solve triangle ABC where AB equals 35 millimeters, AC equals 20 millimeters, and angle C is 45 degrees. Looking at our triangle, we can see that we have been given 2 sides and a non-included angle. So we can apply our sine rule. We can start by trying to find angle B because we have been given the length of the side opposite it. We have also been given angle C and the side opposite to it, so we can select the relevant ratios from our sine rule. So, sine angle B over AC equals sine angle C over AB. We substitute our known values into the equation and rearrange to make sine be the subject. Using the arcsine function on our calculator, we get a value of 23,832 degrees for B. Now that we have 2 angles in our triangle, B and C, we can easily find angle A. We know that the sum of angles of a triangle add up to 180 degrees, so angle A equals 180 degrees less 23,832 plus 45 degrees, which gives us 111,168 degrees. Our last outstanding piece of information is the side BC. Now that we have angle A, we can use our sine rule to find BC and choose our relevant ratios. BC over sine angle A equals AB over sine angle C. Rearrange the equation. BC equals AB times sine angle A over sine angle C. We substitute in our values, so BC equals 35 times sine 111,168 degrees all over sine 45 degrees, which gives us a value of 46,158 millimeters for BC. Lecturers should be aware of the possibility of an ambiguous case for the sine rule. This occurs when two different triangles could be created using the given information. Looking at the diagram, we can see that in this case there are two possibilities for angle C, either an acute angle or an obtuse angle, and hence two possible triangles. The possibility of an ambiguous case can only occur when we are given two sides and a non-included angle. If the side opposite the given angle is the shorter of the two sides, then the side could have two different positions, as shown here. So long as the sum of angle B and angle C is less than 180 degrees, then that possible value for C is valid. There are two valid answers. Let's examine this figure a little more closely. To find angle C, we can use the sine rule. Sine angle C over C equals sine angle B over B. We substitute our known values and simplify to find sine angle C equals 0,955961. We will use arcsine on our calculator to find our reference angle. As sine is positive, we need to look at quadrant 1, where C equals our reference angle, 72,93 degrees. Let's check if this is a valid answer. If we add angle B and C, it adds up to less than 180 degrees, so this solution is valid. We also need to look at quadrant 2, where C1 equals 180 degrees minus 72,93 degrees, which is 107,07 degrees. Checking to see if the answer is valid by adding C1 and B, we find that it is also less than 180 degrees. So this solution is also valid. So in this case, there are two possible values for angle C. Now we move on to the cosine rule. This is also revision from level 3, so students should be familiar with it. Students should remember that we use the cosine rule to solve non-right angled triangles when the sine rule is not applicable. To find sides, we apply these formulae. They change depending on the required side. To find angles, we apply these formulae. They change depending on the required angle. The cosine rule formula is on the exam formula sheet. Students can easily work out the formula for the required angle or side by rearranging this version. Once again, to apply the cosine rule, we need at least 3 pieces of information on the given triangle. The cosine rule is applicable to a triangle when we are given either 3 sides, side, 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 or 2 sides and an included angle, side, angle, side. Looking at this in more detail, if we are given 3 sides, we can find an angle by applying the cosine rule formula with cos of an angle as the subject of the formula. Or, if we are given 2 sides and the included angle, we can find a side by applying the formula with the unknown side as the subject of the formula. Students should remember that the sine rule cannot be applied to these situations. Let's watch how a lecturer teaches an example of solving triangles using the cosine rule.
Solve the following triangle using the cosine rule. You are given triangle ABC with sides C known and the side A known, which means that side B will be here. Now, it is very important to distinguish the difference between an angle and a side. An angle is written in uppercase and a side is written in lowercase. And it's obviously the side opposite to that angle. So if you want to know the name of the side, we must reference it back to the angle opposite to it, which is C. If you want to know the name of this side, we must reference the angle opposite to it, which is A. And remember, your sides are in lowercase and your angles are in uppercase. Find all the unknown sides of this triangle. So what does it mean? Both sides and angles. It means that you must state down first, what do you have? You have side, angle, side. So you can use the cosine rule there because you've got side, angle, side. Which means that what do you have? You have the angle, you have the two adjacent sides, and you want the opposite side to the angle, which makes it b squared is equal to a squared plus c squared minus 2 times a times c, cosine of the angle opposite to this side, which is cosine of angle B. Then B squared is equal to, what is your A squared? Your A squared, your A is 7, so 7 squared plus C squared is 6 units minus 2 times 7 times 6 cos of 120. Straight away we can find B squared here. $127, which is equal to square root of 1, which is equal to B equals to square root of 127. Therefore, B equals to square root of 127, which is our stored answer, is equal to 11 point. We're going to write our answer to 2 decimal places, 25 units, 27 units, not 25, 27 units. Second decimal place is 6, the number following it is 9, so we add 1 to 6 to be 7. We got that, so this is found. Thus making it possible to either find this angle or that angle. We can choose any. Well, let's choose A. So we're going to find angle A, which makes it necessary for us, since we want to find angle A, in this case it's B, then we must start with side A. So that was the first one. The second one is going to be here. So we need A squared now is going to be equal to B squared plus C squared minus 2 times B rather, times C, cosine of angle A. We want to find angle A, so let's make cos A the subject of the formula, which makes it necessary to transpose everything here, starting here. I'm going to transpose this whole side to the left-hand side. The sign changes to be positive. And remember, this is just one term. So 2BC cos of A is equal to B squared plus C squared, which is what you had, minus A squared. Then we want cos A divided by 2BC. 2BC cos A is equal to, let's substitute, what is B squared? So we're going to go back to our graph, to our triangle, and then find B. B is 11.27 squared, which is this, plus, what is your C? 6 units, which is 6 squared, minus, what is your A? 7 squared, all over 2 times B times C. This whole answer, we're going to go and put it here. That's just cos A. Not 0.84304.126. Do not round off at this stage. Why? Because you still want to use this answer to find the angle. Therefore, A is equal to inverse of cosine, or reciprocal if you want to call it, 0.84304.126. So what are we going to do? We're going to say shift cosine of the answer, which was stored in our calculator, close bracket, should be equal to, so angle A is equal to 32.2 decimal places 54 degrees. That's angle A. So you have angle A. What do you have angle A as? So you have angle A as 32.54 degrees. What does it mean? It means that this angle, so angle A plus angle B plus angle C, should be equal to 180 degrees. Why? Because angles in a triangle sum up to 180. Thus making it clear for us that if we say angle C is equal to 180, subtracting angle A, subtracting angle B, our answer should then be angle C is equal to 27.46 degrees. We have solved this triangle.